Hi class. Let's do some more linear algebra. Our goal for this lesson, and many of the lessons to come, will be to prove that the determinant of a matrix is 0 if and only if A is singular, as in A does not have a multiplicative inverse. Like most things, there will be many steps. Here are stepping stones to that fact. Of course, we need a definition of the determinant. So last class, we defined the determinant. We're also going to need to find many different ways to calculate the determinant. Some of these methods will require just inspection. Sometimes we can tell what the determinant of a matrix is just by looking at it as opposed to calculating the determinant from scratch. And 2, we need to find the determinant of elementary matrices. Just to remind you what these are, an elementary matrix is a matrix E such that left multiplication by E performs an elementary row operation on another matrix. Let me remind you what elementary row operations are. That's not how you spell elementary. Our elementary row operations come in 3 flavors. Scaling a row, exchanging 2 rows, and replacing a row with its sum with a scalar multiplication, a scalar multiple of another row. We use these in Gaussian elimination, etc., and we use them extensively to find solutions to systems of linear equations in the past. Let's get back to our task at hand. We eventually want to prove that the determinant of A is 0 if and only if A is singular. To that end, let's start exploring different ways to determine the determinant of a matrix. Here's a question. Does the determinant of a matrix change when we take the transpose? Claim 10. No. The determinant of A is equal to the determinant of A transpose. Before we prove this, let's explore the idea. If I have a matrix A, B, C, D, E, F, G, H, I, and I compare it to its transpose, going up from the top to the bottom, A, B, C, D, E, F, G, H, I. I can find the determinants of these matrices. I can do the cofactor expansion along the first row of A to find the determinant, and I can compare that to the cofactor expansion along the first column of A transpose to find the determinant. Let's do it. The determinant of A going along the first row is going to be A times the determinant of what's left. So E, F, H, I is in the matrix that's left when I remove the row and column that A is in. Minus B, D, F, G, I, plus C, D, E, G, H, determinant. Compare that to the determinant of A transpose, moving along the first column. Again, we get A, but then we get the matrix EH, FI, minus B, DG, FI, plus C, DG, E, H. In order to talk about what's going on here, I'm going to draw our attention to these smaller matrices and introduce some new notation. EFHI is M11 of the matrix A, but I need to make a distinction between the M's of matrix A and the M's of matrix A transpose. So I'm going to add a little annotation here. So EFHI is M11 of A, EHFI is M11 of A transpose. This over here is going to be M12 of A, and this is going to be M13 of A. And down here, correspondingly, I'm going to have M21 of A transpose and M31 of A transpose. Notice that the determinants of these smaller matrices are equal. We're going to get EI minus FH. Here we get DI minus GF. And for M13 of A versus M31 of A transpose, we're going to get DH minus EG. Here's what I want you to take away from this. Two things: that in this case, the determinant of A is clearly going to be the determinant of A transpose. And the key to this calculation is the fact that Mij in A, the transpose of that is precisely Mji in A transpose. That's the idea. Let's actually prove our claim. Claim 10. The determinant of A is equal to the determinant of A transpose. Proof. We're going to do this proof by induction. In particular, we're going to induce on N, where A is an N by N matrix. So we induce on N. As in any inductive proof, first we establish the base case for N is equal to 1. A is a 1 by 1 matrix, therefore A is simply the matrix with a single entry A11, which by the degeneracy of this case is its own transpose. So certainly A is equal to A transpose, and the determinant of A is equal to the determinant of A transpose. Setting up the inductive hypothesis, we're going to assume that this fact holds true for all matrices up to K by K matrices. And then we do the inductive step. Assuming it's true for K by K matrices, we will prove it is true for K plus 1 by K plus 1 matrices. Just like in the idea, we're going to do the cofactor expansion for the determinant of A along the first row. And using sigma notation, we're going to realize that this is the sum of -1 to the I plus K of the entry, the ikth entry, times the determinant of M, I, K, this mini matrix in A, as K ranges from 1 to N. What I want you to notice is that MIK is the matrix derived from A by erasing the ith row and the kth column. This means that by the inductive hypothesis, its determinant is the same as its transpose. So we can replace this determinant by the determinant of the transpose of this matrix by the inductive hypothesis. And then, as we noted before, the transpose of that mini-matrix corresponds to a matrix in A transpose. The last thing that we have to realize is that AIK, the ikth entry in A, is the kith entry in A transpose. Putting this all together, we'll realize that this is just the formula for the determinant of A transpose using the cofactor expansion along the first column. QED. End of proof. So we've proved something about determinants and how they interact with taking the transpose. Let's ask another kind of question. Is it easier to calculate the determinant of A if A has a special shape? Let me make this clearer. In claim 11, the determinant of a triangular matrix is the product of the diagonal entries. The claim is that when we have a triangular matrix, it's much easier to calculate the determinant. You just multiply the entries down the diagonal. As before we actually prove this, I want to communicate the idea. And for this particular fact, this claim, the idea is particularly visual. If I had, say, a lower triangular matrix, what does that look like? I've got entries going down the diagonal, perhaps. I've got entries below the diagonal, and everything else is a zero. And say I want to find the determinant of this matrix. I'm going to expand along the first row, which means I'm going to take A11, erase the column and the row that's in, and then multiply by, of course, the determinant of the matrix that's left. So this is going to be A11, of course, times -1 to the 1 plus 1, which is just 1, times the determinant of this red matrix, which, luckily enough, happens to also be a lower triangular matrix. If I were to continue the cofactor expansion, I'm just going to get zeros, since it's zeros all along here. How do I find the determinant of this matrix? Well, as before, I'm going to go along the first row. I'm going to take this entry, which is A22 of the original blue matrix, erase the column and the row that it's in, and then multiply by the determinant of the matrix that's left. So this is going to be A11 times -1 to the 1 plus 1 times this lower triangular matrix, which of course is just A11 times the determinant of this lower triangular matrix times, sorry, 822. I'm missing my 822 because that is 822. Following this idea, if we just rinse and repeat, we should just get all the diagonal entries of the original matrix. Let's actually prove it. Claim 11. The determinant of a triangular n by n matrix A is the product of its diagonal entries. Proof. Saying that a matrix is triangular is not particularly specific because there are lower triangular matrices, upper triangular matrices, strictly upper, strictly lower triangular matrices. I don't want to have to prove this for every kind of triangular matrix. So I'm going to pull in claim 10 to help us. By claim 10, the determinant of A is equal to the determinant of A transpose. And what is the transpose of an upper triangular matrix? It is a lower triangular matrix. So without loss of generality, we may assume A is lower triangular. Now let's get on with the proof. We're going to do a proof by induction, and we're going to induce on n, where A is an n by n matrix. We establish the base case, n is equal to 1, and we'll notice that if A is a 1 by 1 matrix, this is what it looks like, and the determinant of A in this case is defined to be A11 by definition. Our inductive hypothesis is just to assume that this works up to n is equal to k, as in it works for k up to k by k matrices. And then we're going to do our inductive step. Assuming this works for k by k matrices, we will prove that it works for k plus 1 by k plus 1 matrices. Let's talk about the determinant of A. Using just the regular cofactor expansion along the first row, this is the formula. But recall that A is lower triangular, so A12 is 0, A13 is 0, all the way up to A1n. So what we actually get is A11 times big A11. Let's remind ourselves what big A11 is. We're going to have A11 times negative 1 to the 1 plus 1 times the determinant of M11. And let's just recall for ourselves that M11 is a K by K matrix. By the inductive hypothesis, the determinant of M11 is going to be the product of its diagonal entries. So out here we get A11, negative 1 to the 2 is just 1, and the determinant of M11 is going to be A22 times A33, etc., all the way to A k plus 1, k plus 1, by the inductive hypothesis. End of proof. QED. Let's do some examples. Example. Let's talk about the identity matrix of any size. It's a triangular matrix. 1's down the diagonal, 0's everywhere else. So no matter what the size, by claim 11, the determinant is going to be 1. Example. Let's look at the matrix 8, 0, 0, 3, 1, 0, 4, 5, 0, and find the determinant. This is indeed a triangular matrix, which means we only need to pay attention to the diagonal. The determinant of this is going to be 8 by 1 by 0 which is 0. Let's do some exercises. Exercise. Find the determinant of this matrix 3, 0, 0, 5, 4, 0, 8, 2, 1. Exercise. Let's find the determinant of this matrix 0, 0, 1, 0, 4, 5, 3, 2, 8. At the tail end of this lesson, I imagine that there's going to be a lot of lingering questions. One that has less to do with the content than the form of this lesson is the fact that we did a lot of inductive proofs. So you should be asking yourself, can you execute a proof by induction? We're going to get lots of practice on this. Other things that one can ask, are there other shapes of matrices? Whose determinant is easy to calculate? And last but not least, in reference to our ultimate goal, what are the determinants of elementary matrices of types 1, 2, and 3? Think on this. See you next time.